session for today. So this is the second class of the nuclear and particle physics course. So at first I am going to share my screen so that you can see. Okay, this one. Wait. Can you see my screen? Can anyone confirm?
Yes, ma'am.
Okay, thank you. So this is the second week question assignment. Okay, if you people were not present in the previous class, I would like to tell you one thing that I am not the course instructor and all. Like course instructor is Professor Paulus Paulus, as you can see that it is written here. And basically what I am the PMRF NPTEL teaching assistant, and what I will do here, I will just discuss the question and answer part of the previous year assignment part of the course nuclear and particle physics. And as you all know that it is a 12-week course, so that means each and every week there will be 2 hours class, and in that 2-hour class there will be the just question answer discussion will be there. So the thing, whatever the theory part, whatever it is there, it is already described by Professor Paulus Paulus, and it will also be described by Professor Paulus Paulus in the next week towards. So what I will do, I will just discuss the question and answer part of that course. So let's start today's session. So in the today's session there will be the question and answer session of assignment 2, week 2 of the previous year question, not obviously this year question. Okay. So this is the let's say we are having a question here. You can see that there are more than 6 or 7 questions. I think in the previous year question there was only 6 or 7 questions, but obviously in 2 hours 6 or 7 questions is too much little in number. So that's why we have increased the number of questions so that we can discuss more and we can understand more on the topic. Okay, so this is the first question. The first question, you can see that it is written as what is the expected spin value of the ground state of the nucleus nitrogen 715 within the nuclear shell model, and we have 4 options: 0, half, 1, 3/2. And also one more thing I would like to tell you that if you have any type of doubt, you can just unmute yourself and you can ask me the question at that time. No need to wait or no need to raise your hand or all that things. Because I am just presenting my screen, so that's why if you are going to raise your hand also, I could not see. So it's no need to raise your hand in Google Meet. If you have any doubt, you can just unmute yourself and you can ask me the question at any time. Okay. Okay, because basically this session is nothing but only one side discussion. It should be a 2 types of discussion. Like you can ask me something or you can give me some suggestion on that also. That will be very much appreciable. So like in this course and in this session we will just discuss something about the nuclear and particle physics course. Okay. So basically now coming to the first question. So in the first question it is saying that a nuclear shell model is there, and as per the nuclear shell model, what will be the ground state spin value of the nucleus nitrogen 715, and there are 4 options. Okay.
Ma'am, the
So
screen is not visible.
yes, tell me.
The screen is not visible.
Screen is not
The
visible.
screen share is stopped, ma'am.
Okay, wait. Okay, okay. Ah, okay, maybe my internet was not that much stable, so sorry for that. I'm just joining again. Ah. Now, can you see my screen?
Ma'am, you're muted.
Sorry, I thought that I was unmuted. So, can you see right now the screen?
Yes, ma'am.
Okay.
Yes.
So, I mean, in between my talk, it was disconnected or what? Like, you people had something, or you people did not heard anything. I think you have heard something, right? Like, I was talking, and I don't know that at which time that network has disconnected. So, okay, so whatever it is, I will just repeat this thing. So, the repeating this, I just want to know the question. The question is, in the nucleus cell model, within the nucleus shell model, what will be the spin value of the ground state of nucleus nitrogen 715? Okay, so this is the question, and we have four options on that: 0, half, 1, and 3 by 2. So, before going to the answer of that question, I would like to tell about the nucleus cell model. What is nucleus cell model? I think you all have known this one because in this week only Dr. Paulos have already mentioned that what is nucleus cell model, right? So, like, nucleus cell model is nothing but a very similar of the atomic cell model of the atomic structure. I mean, atomic atom. So, to describe the structure of the nucleus, we are going to construct a model which is known as nucleus cell model. And why nucleus cell model? Because it is basically a cell. Like, energy cells are there. There are so many energy cells. So these like, there are so many energy cells are presented here in the nucleus, inside the nucleus. So these are the energy cells of the nucleons. Each and every nucleons we can have that energy cells. So if we are constructing our nucleons in such a way that our nucleons can have in specific energy cell, then we can have a nucleus shell model. Before that, there was another model which was known as semi-empirical mass model. I think most of you have already heard that one, and in the previous week also it was described. But in the semi-empirical mass formula, what was there in the semi-empirical mass model? There was, I mean, the assumption was that the nucleus is nothing but a circle. I mean, it's like a ball. Okay, but in nucleus cell model we are not doing that one. In nucleus cell model we are assuming that inside the nucleus, each and every nucleons have certain energy levels, and according to the Pauli exclusion principle, these nuclear cell models, nuclear energy cells are structured. So, according to the Pauli exclusion principle, the nucleons will be set in these each and every energy cells. That is the nuclear shell model. Explain, like, little bit of explanation. So, what will be the structure of that energy levels? The energy levels can have just very similar to atomic model. You can have like 1s half, 1p 3 by 2, 1p half, then 1d 5 by 2. I have that full energy range of that nuclear cell model. I will show you a little bit later. But yeah, this type of energy levels will be there for each and every nucleon inside the nucleus. That is the nuclear cell model. And according to the nuclear cell model also, we can have so many advantages. Like, we can tell that if this nucleus is stable or not, what is the spin of that nucleus, what is the ground state spin, what will be the first excited state spin, or what will be the parity of that nucleus. We can say all the things, right? So we will see this one. So in the first question, what it is asking, they are asking the spin value of the ground state of nucleus. So we do not need to go the first excited or second excited state of that nucleus. We will tell about these things in next questions. But right now we will only focus on the ground state of nucleus nitrogen 715. And we want to know that what will be the value of spin for that according to the nucleus cell model. Okay, now this is 715. So I am just going to write this one, N nitrogen 715. That means you can all know that this is the what is the importance of that notation. The importance of that notation is the proton number will be 7. Proton number is 7, and mass number is 15. So what will be the neutron number? Neutron number will be mass number minus proton number, that means 15 minus 7, that means what, 8. So basically according to that notation we can have some information about the proton number, mass number and the neutron number. So the proton number is 7, mass number is 15 and neutron number is 8. So what is nucleon basically? Nucleon is basically nothing but the combination, the proton or neutron. So we will focus on the proton as well as neutron. So you can see that there is proton number 7 and neutron number 8. So as neutron number is 8, which is even and it is half filled, then we will not consider 8 in our calculation. We will only consider number of protons in our cell model structure to get the spin. Okay. So what is this? Like I have already written here that for nitrogen number of neutrons is 8, which is even, that is half filled. So and number of protons is 7. So the orbital configuration for ground state will be coming from the proton number only. So the proton number, as already we have mentioned, it is 7. So we can divide the 7 in a very sophisticated cell structure model. This is the notation of that cell structure. That means 1 is half 2, 1 p 3 by 2 4, 1 p half 1. So what is this 2, 4 and 1? This is nothing but the number of nucleons in that energy state. I have already mentioned you here that these are the energy states. Okay, so this is, let's say 1 is half. So in that 1 is half, max to max 2 nucleons can be present. Obviously according to the Pauli exclusion principle. So that means this can be like that. Okay, now it is coming that 1p 3 by 2. So in that case 4 can be there. 1, 2, 3 by 4. Okay. So how we are getting that one? 3 by 2 into 2 plus 1. So that means 4. Right? 3 plus 1. That means 2s plus 1. Whatever it is there, this is the spin value, right? So 2s plus 1 will be the number of nucleons in that energy level. So here you can see that 1 is half is there. That means spin is half. So that's why our number of nucleons will be in that 1 is half energy state will be 2 into half plus 1, that is 2. So that's why we have written here 2. Max to max 2 nucleons can be there. If there is a lack of nucleons, then it can be 1, but it cannot be 3. Max to max it will be 2. Okay. Now very similarly 1p 3 by 2 4, 1p half. Okay, now you can see that here half is there. So obviously how many nucleons can be there at most? It can be 2 because half is there. But as we have proton number 7, that means 2 plus 4, which is 6. Then obviously 1 nucleon is left. That means it should be 1, not 2. So our outermost cell, which is 1p half, it is half filled. It is not full filled. Like if full filled is there, then it will be 2. But if as it is a half filled, then there is 1. So if it is a 1, that means our spin of the ground state will be contributed only from this portion, that 1p half. 1. So only this outermost cell will be responsible for having the spin of the ground state of nitrogen 715. So what is the spin of that? The spin will be, it is already mentioned here, half. Half. So that's why the result of this answer will be half, and it is, I think, in B. Yes, it is in B. So that's why the correct answer will be B. I think you all have understood that one, or should I mean, obviously in second question also, if you just read the question, that is a very simple, very similar of the question number 1. So if you don't understand that one, we can also discuss in these questions also very clearly. So the first question had an answer of half, right? Now coming to the second question. Second question is a very similar one, that what is the expected spin value of the ground state of the nucleus calcium 2043 within the nucleus shell model. So according to that one, we have to just calculate a very simple, a very similar thing, whatever I have done here, 20, 43. Then you can see that proton number is 20, neutron number is 43 minus 20, which is nothing but 23. So as this is an even number, we will not consider about proton, we will just consider about neutron. So in that neutron 23, we have to mention, we have to fulfill the 23 with the nuclear cell model. So what will be the nuclear cell model for that? I have already mentioned here. Okay, I can show you one thing so that you can have the idea. Yeah, this is the thing. So you can see here, 1s half, we have to go from lower to upper portion. Okay, that means 1s2, 1p 3 by 2, 1p half, 1d 5 by 2, 1s2, 2s half, 1d 4 by 3 by 2, and like that, 1f 7 by 2, like that we have to go. So that means at the very first we will write like that, 1 is half 2, then 1p 3 by 2 4, 1p half 2, then what is that, 1d 5 by 2 6. Why 6? Because 5 by 2 into 2 plus 1, that means 6. Then 2 is half 2, again 1d 3 by 2 4. Now up to that, what is the nuclear number? 2 plus 4 plus 2, that means 8, plus 6 14, plus 2 8 16, plus 4 20. That means up to this one it is already 20 has done. Now you can see that in the calcium question, yes, in the calcium question, what is the number of neutron we need? 23. So 20 has already done. So that means 3 are left. So 3 will be in the next higher energy state. So what is the next higher energy state? The next higher energy state is 1f 7 by 2. And this will be 3, because we need 3 more nucleons above 20. Okay, so that means you can see that up to these, all the states are fully covered. Only this state is not fully covered. So the last one will be the responsible for giving the spin of that system. So what will be the spin for that? 7 by 2. And we are also considering only the ground state, so that means we are not going to the first excited or second excited state right now. So for the second question, what will be the answer of that? The expected spin value of the ground state of nucleus calcium 2043 within the nuclear cell model will be 7 by 2. Is there any question? If you have any question, you can just immediately ask me, no problem on that. Okay. So this class will be totally based on the nuclear cell model. So we will go a little bit slowly so that you can understand line by line. So these two are very similar ones, so that's why I have written these questions simultaneously. Now coming to the third question, is if there is no question, then we can move to the third question. I think there is. Okay? Hello? Oh, I think my internet is not that much stable. Can you hear me?
Yes, miss.
Oh my god. Did you hear these things, whatever I told, or not?
No, ma'am.
No, my first used.
Like when the internet got disconnected, I couldn't
Ma'am,
understand.
while you were explaining the first question and describing the mass number and the number of protons were disconnected.
Sorry, I can't hear you properly. Can you please repeat?
Ma'am, when you were discussing about the number of protons for the first question, you were disconnected.
Oh my god, from the first question it was disconnected, and after that you did not hear anything.
No, ma'am.
Oh, I thought that you people are hearing all the things. Okay, sorry for that. I don't know what is going with my internet today, but yeah, sorry. So, okay, should I explain again? Okay. Okay. Okay, so the first question was what? The first question was what is the expected spin value of the ground state of nucleus nitrogen 715 within the nuclear cell model? So, I mean, whenever you will be disconnected or I will be disconnected, just remind me, or how can you remind me? Okay. I don't know what is the problem with my internet today. Okay, so in the first question, what was the question? In the nitrogen 715, what will be the spin value of the ground state? Okay, so 715 means I have already written here the number of proton is 7 and mass number is 15. So number of neutron will be 15 minus 7, that is 8. Right. Now as you can see that there is a number of proton and number of neutron is 7 and 8. So in the cell model, as I have already told you, in the cell model we will consider about the nucleons. So nucleons is nothing but the protons and nucleons and neutrons. I mean, as a whole these are called as nucleons. So we have to focus on proton number as well as neutron number. But as you can see here, the number of neutrons is 8, which is even number and which is half filled. So that means it is a more stable nuclear shell structure. So we will go only for the number of proton, which is 7. So the orbital configuration for the ground state can be written as like that. So what I can write here, like these are the nuclear cell notation. Like if I have a new energy cell, so this is the energy level. In that energy level I have written one notation. What is the notation here? This is the S, means the L value. L value is orbital angular momentum value is S. Then half is spin angular momentum, that means the spin value is half in that energy level. And what is 1? 1 is the number of, N is the number of principal quantum number. So N, L and then S. It is like that. This is the structure of that atomic energy level. Nuclear energy level, not atomic energy level, nuclear energy level. Can you still hear me or has it disconnected? Hello.
Yes, ma'am.
Does anyone know if the sessions are recorded? Yes, the session is recorded, but I don't know today what is the problem with my internet. So, but the session is recorded, so you can have the recorded.
Ma'am, how will we access them?
Oh my God, what is happening with my internet? Can you tell me once again what you told?
Ma'am, how do we access the recorded sessions
Yeah,
for those
I
who
think
will
NPTEL coordinator will send you the link of that. But if he or she will not send anything, then you can just search in Google my name. Then you can have the recording of that. Okay, that's a
Okay,
very
ma'am.
simple one. And could you send the first one? The first one send me the it is already in the YouTube, so you can just search my name and you can find it. There is the first one is already available there. Okay. I mean, why it is that much unstable today? I don't understand. Okay, it's better to discuss right now, but I don't know when you people will be disconnected again. Can you see the screen?
Yes.
Yes, ma'am.
Okay. Okay, so the orbital, okay, so what I told, yeah, so the number of neutrons, I'm still in first question, see. So in first question you can see that nitrogen 715 is there. Like, you people did not heard about anything on that second question, or you people were totally like, I was totally disconnected when I was describing first question. Can you confirm me?
Ma'am, you got disconnected when you were discussing the first question.
First question, okay. And after that, like, I already discussed second question also, so I don't know. Okay.
Yes, ma'am, you were disconnected for quite a long time.
Oh, really? Actually, I couldn't understand that I was in disconnected mode. So, yeah, fine. Okay, so the first question was, I think, okay, in the first question, as I already told, that according to the notation N715, the number of proton is 7 and mass number is 15. Okay, so number of neutron will be A minus P, that means 8. So now what we will do, we will focus on the nucleons. So nucleons means what? Nucleons means the proton number as well as neutron number. But you can see that the neutron number is even number, so this is half filled nuclear structure. So we will not bother about neutron number, we will only bother about proton number, okay, which is odd in number. Now coming to the cell structure. So what will be the cell structure for that? So you can see that the number of proton is 7. So that means the orbital configuration for the ground state will be like 1s2 half, 1s half 2, 1p 3 by 2 4, 1p half 1. So how these sessions, how the energy levels has come? Can you hear me?
Yes, ma'am.
Yes, ma'am.
Okay, I thought that again I disconnected. Okay, so how these terms are coming here? Let's say 1 is half. Okay, let me clear all these things, as I am not disconnected, so I can tell right now clearly. Okay, so let's say these are the very important and very interesting portion, so that's why I wanted to discuss you a little bit more. So this is okay. So each and every energy level has some structure, has some notation. What is the notation of that? The notation will be N, L, then S, and then number of nucleons. So what is these things? N is the principal quantum number, L is orbital angular momentum, S is spin angular momentum, and capital N is number of nucleons in that energy level. That is the general notation of that each and every energy level. So now let's say I am writing here 1s half 2. Then you can have an idea that 1 means the principal quantum number is 1, S is nothing but the L value. So why L value is S? You can have a series that if L equals to 0, then we can have S. L equals to 1, then P. L equals to 2, SP, D. Then L equals to 3, F. L equals to 4, G. Like that. Okay, then 5, H. So this type of L value is there. Now this is S value. S is nothing but spin angular momentum. So if spin angular momentum is half, that means this energy level has S equals to half. And what is 2? 2 is nothing but number of nucleons in that energy state. So you can see that how we can have the 2 value. Can you hear me?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, so how this 2 is coming? 2 is the number of nucleons in that energy state. How it is coming? It is coming with 2s plus 1, this expression. So what is S here? S is spin orbital momentum. So as you can see that in that energy level, spin orbital momentum is half. That means 2 into half plus 1. That is 2. So that's why the maximum nucleon can have in that energy level will be 2. But it can have 1 if there is no other nucleon, right? But here for that number of protons is 7, then we can have the orbital configuration for the ground state is like 1s half, In that 1s half, 2 nucleons will be there. Now coming to the next one is 1p 3 by 2, and here 4. How it is 4? 3 by 2 into 2 plus 1. Okay. Now 4 will be like there 1, 2, 3, 4. These 4 nucleons are already there. So 4 plus 2 as a whole 6 nucleons are already there. Now 1 nucleons are left. Which nucleon will be in the next energy level? So what is the next energy level? The next energy level is 1p half 1. Okay, so this is the next one. So in that energy level, you can see that the spin is half. That means at most 2 nucleon can have in that energy level. But as we don't have 2 left nucleons, then we have only 1 left nucleon. That means that one nucleon will be kept here. So now how can I find the spin of the ground state? The spin of the ground state can be determined by the outermost energy cell. What is the outermost energy cell here? 1p half. And what will be the spin for that? As I already told you, spin is this one. That means the spin will be half. Can you hear?
Yes.
Yes,
Okay.
ma'am.
Okay. Sorry to bother you people. So that means now the correct answer will be B, which is half. Do you understand that one? Because like it's a very similar, the second question is very similar to the first one. So I can also skip the second question also, but yeah, I have already described that one as you people did not hear anything, so I can tell again. Okay, now coming to the what is the expected spin value of the Brown state of nucleus calcium 2043 within the nuclear cell model. This is a very similar one as I have already mentioned in the nitrogen 713, I think. 713 or 714? 715. 715 case I have already mentioned, but still I can just tell you a little bit. So here they are asking about the calcium 2043 nucleus and what will be the spin value of the Brown state of the nucleus and within the nucleus cell model. So just we have to calculate quickly that what is the neutron and proton number. Neutron number is, you can see that 43 minus 20, which is 23, and proton number will be 20, and the atomic mass number is 43, right? Now as you can see that the 20 is the even number, so we are not talking about this one because it is a fully filled energy state. Now we are talking about 23 only. So in the 23 we will have the energy levels configuration. So what will be the energy level configuration for that? Let's say I have, okay, for that I went here. Can you hear, or I am disconnected?
No, ma'am, I can.
Okay. Okay, so this is the energy level diagram for all the nucleons. So you can see here that at the very first one is half was there as I already written there. Then 1p 3 by 2, 1p half, 1p 5 by 2, 2s half, like that. So we need 23 number. I mean the nucleon number should be 23. It should be fulfilled. Okay. So how we can have the 23? You can see that from this to this, I mean from 1s to 2s energy level, it is 20. Already the 20 has already done. So we need 3 more. That means we have to go to this one. This energy state. What is this energy state? 1f 7 by 2. So 20 has already done, but 23 we need. That means 3 more nucleon we have to put in that 1f 7 by 2. And how many can be there in 1f 7 by 2 energy level? 2 into 7 by 2 plus 1. That means 8. So at most 8 neutron can be present in that 1f 7 by 2 energy state. But we need only 3. That's why we are writing here 3. Right. So what the outermost energy cell is what? 1f 7 by 2. And what is the spin for that? The spin for that is 7 by 2. That means our result will be 7 by 2. Do you understand?
Yes, ma'am. Ma'am, what will happen if both the proton and neutron number are even?
Yes. In that case, let's say I have C612. You know this is a very simple one, carbon 612. For that neutron is also 6 and proton is also 6. So for that the spin number will be 0 because it's a stable energy, stable quantum energy level. So that means for spin will be 0, right? Okay.
Okay, ma'am.
Yeah. So now coming to the third question. In that third question, you can see it's a very similar question, that what is the expected parity of the ground state of the nucleus, this one in cell model. So now we need to know what will be the parity. I mean, till now we were discussing about the spin value, but right now we want to know what will be the parity for the nucleus. So what will be the parity for nucleus? Say silicon 1429. Just we have to quickly do that one, that proton value is 14, neutron value will be 29 minus 14, how much will be it is 15, right? Okay, now you can see that this is even number, so we will not talk about this one, we will only talk about 15. So coming to the energy configuration, quickly, 1 is half 2, 1 p 3 by 2 4, 1 p half 2, 1 d 5 by 2 6. Now come to the number, how much it should be? 15. Okay, 2 plus 4 6, 6 plus 2 8, 8 plus 6 14, right? Now we have to go another one. So what will be that one? 1d 5 by 2 and after this 2s half is there. Yes, 1d 5 by 2, then 2s half. Then we have to write here 2s half. 2s half. But how much it will be? It should be 2 because for fully filled, but it will be 1 because we have only 15 nucleons. So these are 40 and this one is the extra one. So now you can see that from the previous two questions we can have the spin is half. But what will be the value of parity? Parity is nothing but minus 1 to the power L. So we need to know what will be the value of L here. L will be 0 here because I already told you L is 0 means S value, 1 is P, 2 is D, 3 is F, like that. Okay. So if S is there, that means L will be 0. So that means minus 1 to the power 0, which is nothing but a positive value, right? I mean that even. So that's why we can have the answer of that is even. What is the expected parity of the ground state? It will be even. Is it understandable?
Yes, ma'am.
Okay.
And what will happen if both the proton and neutrons are odd then?
Both proton and neutrons are
Odd numbers.
odd numbers. Okay, if both are odd number, then we have to consider both of the nucleons separately. Let's say, okay, let me tell you. Let's say I have like nitrogen 7. What will be the 16. Then number of proton is 7. Number of proton is 7. Number of neutron is what? 16 minus 7. What is that one? 9. Right?
9.
So for that we have to consider 7 as well as 9 in this nuclear shell model. Let's say for 7 there will be one structure like that one, right? And for 9 also there will be another one. Then there may be something as the outermost. Okay, let's say this example. Then what will be the 7? 7 means what? 7 means 1 is half 2, 1 p 3 by 2 4, and then 1 p half 1. So this is for proton equals to 7. Now come to the neutron equals to 9 part. What will be that one? This one will be 2, 1 p 3 by 2 4, 1 p half 2, and then 1 d 5 by 2 1, because 6 no yes 8 9 yes. So for proton the outermost cell is 1 p half, but for neutron the outermost cell is 1 d 5 by 2. Now what we will do here, if for that case, for the N716 someone wants to ask me about the spin, then what I will do, from these outermost what is the spin? The spin is half, and from these what is the spin? The spin is 5 by 2. That means now my total S will be from half minus 5 by 2 to half plus 5 by 2 in step of 1. That means what is the value of this? This is like 2 to 3. That means the 2 value will be there and 3 value will be there. Can you hear me?
Yes, ma'am.
Okay, fine. So for that case, I mean when the neutron and proton will be odd, then we have to combine these two outermost energy level so that we can have the resultant spin angular momentum. And this resultant spin angular momentum will be S1 plus S2 or S1 minus S2 to S1 plus S2 in the step of 1. So here you can see that 2 to 3, that means obviously 2 or 3, these two value can be possible for the total spin angular momentum of the nucleus nitrogen 716. Do you got my point?
Yes, ma'am.
Okay, fine. Now coming to the fourth question. I think that third question has already done. Yes, third question is already done. It is even number, right? The fourth question is also very similar to the third question. What is the expected parity of the ground state of the nucleus magnesium 1225 in cell model? Okay, so what will be this one? So very simply, magnesium 1225, we have to write that one. Then what is this? Proton 12, proton is 12, neutron is 25 minus 12, that is 13. So as usual, we will not consider this one, we will just only consider this one. So then what will be there? That let's say 13. 13 means what will be the configuration? 1 is half 2, wait a minute actually. Again I was disconnected or not?
No, ma'am.
I think again I was disconnected, right?
No, ma'am.
No. Okay, I thought I was disconnected. Okay, wait, because my charge is going down. Okay. Can you see the screen? No.
Yes, ma'am.
Yes.
It is.
Okay, you can see that screen. Okay, fine. So here, yeah. So what I was telling, yeah. So for that magnesium 1225, what will be the energy configuration? 1 is to half, 1p 3 by 2 4, 1p half 2, 1d 5 by 2. See how much it is? 2, 6, 8, and then 5 we need because it is 13. So now you can see that there will be the maximum number as 6, but we don't have 6 nuclear, so that's why we have written 5. So what will be the parity of that? Parity will be minus 1 to the power L. Then you have to tell me what will be the value of the parity for that, because what is the value of L here? Can you tell me what is the value of L here?
3.
Not 3. D is what? See, I think
L equal to 2.
L
Two, ma'am.
0, 1, 2, 3, 4, 5. Okay. S, P, D, F, G, H. It is like that. So you can see that there is D. So D means L will be 2. That means it is a positive parity. That means even parity. Okay. So the question, the right answer will be even here. Okay, fine. Now coming to this one, this is a little bit tricky question. Okay, you can see that this is a very similar one, whatever we have told in the previous questions, but it's a, do you have any question? You can tell me. Someone is unmuted. Okay, so do you have any question? You can tell me, no problem. Okay, so coming to the question number 5, it is a little bit tricky question. You can see the question very carefully. Within the nuclear shell model, spin and parity of the first excited state of carbon 613 are. Just this is a very tricky one, that first excited state. Ram Babu, can you please unmute yourself? Mute yourself, or if you want to ask something, you can ask me. Okay, thank you. Yeah, so within the nuclear cell model, spin and parity of the first excited state of carbon 613 will be what? Okay, so till now we were bothering about the ground state only. Now we will go for the first excited state. Now at the very first, what we will do, very similarly we will do like neutron number and proton number. Proton number is 6, neutron number is 13 minus 6, which is 7, right? Okay, I have the place. So now as proton number is even number, we will not consider that one, we will consider about the neutron number. So now we have to know what will be the first excited state. Let me write the ground state at first for neutron, right? So what will be the ground state for the neutron? 1s half 2, 1p 3 by 2 4, 1p half 6 1. Okay, this is the ground state. This is the ground state for carbon 6 13 and neutron number 7. This is the ground state for that one. Now they are asking for the first excited state. Then what will be the first excited state? Now I can have a picture of that. Let's say I am writing down like that. Okay, so this is 1s half, 1p 3 by 2, 1p half, and above that what is there, you can see from that figure, 1 is half, then 1p 3 by 2, 1p half, then 1d 5 by 2, right? Then 2s half. Then okay, so that means 1d 5 by 2 is there. So now I am putting all the nucleons here. At the very first 2 nucleons will be there, then 4 nucleons will be there. Then this is the one. This is the ground state configuration. Now coming to the first excited state. So what will be the first excited state? As usual, first excited state, the first one will be the same one. Now these 2 and these 3 are the important one. Let's say it may be there may be 2 options in the first excited state. Can you hear me, or am I disconnected? Can you hear me? Hello, again I was disconnected, sorry for that. Did you hear anything on the last question or not? I am going to share so that you can tell me. Did you hear anything on that or not? Did you hear on that question? This. Did you hear anything?
Yes, ma'am.
So, like, up to which portion you have heard? Did you heard that the ground state configuration is like that? No or yes?
Yes, ma'am.
Okay. So now coming to the first excited state. What will be the first excited state for that? So you can have that first excited state means the first energy level is like that, whatever it is. Then these 2 and these 3. So there may be 2 options. One option can be like that. This nucleon can go here. That may be a possibility for the first excited state. Or there can be another possibility. The another possibility is what? This will not go here. This will go here. Okay. So the 2 possibilities there. One possibility is this can go to higher state, or this can go to the, among of these 4, one can go to the higher state, and this will be putting as whatever it was previously. So these two options may be there. Can you hear me?
Yes, ma'am.
Okay, fine. So these two options can be there. Now how can I understand that which one option will be there for the first excited state of carbon 613? Okay, for that answer we have to see the energy gap between these levels. Let's say I was telling about what? I was telling about these two options. One option was this outermost nucleon can go to here, or among the four one can go here, and this was the previous one and it will not go here. So these two options I was telling. So you can see from that figure that 1p 3 by 2 and 1p half, the energy gap between these two are very less, but 1p half and 1d 5 by 2 has a very large energy gap, right? So for first excited state, it is very much possible to go among the four nucleon, one can go to the higher one and this will not go to that one. Do you understand this option? Like the second option will be most probable, because you can have the from the picture that 1p and 1d the energy gap is very much compared to 1p half and 1p 3 by 2. So whenever the first excited state will be there, that means it will, I mean the this nucleon will not go to the 1d 5 by 2, rather the 1p 3 by 2 one nucleon will go to 1p half. Is it clear, or should I write here clearly? Hello? Hello?
Yes, ma'am.
Okay.
Yes, ma'am.
So, like, do you understand? Okay. See, basically, there was two options. I told you. This can go higher level, or among these four, one can go to that level. But as you can see from the energy level diagram, the energy gap between these two are very much than these two. So obviously most probable option is which one? Most probable option is this can go to this portion, I mean this energy level, not this to this. Okay, so for that, for carbon 613, the first excited state will be like there will be 3 nucleon and this one will go here, and whatever it was there previously in 1p half, that one nucleon, it is like that, but this nucleon will go here. So what will be the modified version of the first excited state? 1s half to 1p 3 by 2 3. Now it is no longer 4, it is 3. Now 1p half 2, because here it is fully filled. Now you can see that what will be the speed and parity of that energy state. You can tell me, like, see here which one is the unfilled one. This one is fully filled, this one is also fully filled, this one is not fully filled. That means for the spin angular momentum, this one will be responsible. So for that case, the spin will be 3 by 2, and for that case also the parity will be minus 1 to the power L, which is minus 1 to the power 1, because P is 1. P value is 1. That means it is odd. So the 3 by 2 and odd will be the answer for first excited state of carbon 613. 3 by 2 and odd. Do you understand my point? Hello? Hello? Again I was disconnected. If we don't remember that energy diagram, then there is any formula or method. Okay. See, basically, yeah, I just want to tell the answer of that Shubham questions. If we don't remember that energy band diagram, then there is any formula or method to calculate the energy gap. So yeah, basically whatever it is there, most of the cases we don't consider this energy gap. Unfortunately, your answer will be no. Like we don't know any exact formula or method to calculate the energy gap. We have to see these things, whatever it is there. Yes, we have to see this diagram, and after that we can find the energy gap, which one is that one or which one is this one. But we have a good news also. The good news is like that whatever I have given as a example C613, it will not be, I mean, like there is 0.01% chance in your exam that that type of questions will be coming, because this is nothing but coming from the energy gap, as I already told you. But in most of the cases, in such a situation, you can find in most of the cases the first excited state or second excited state will be in between these small energy levels. Not it is like that from here to here or here to here. It will not be there. Okay, but I have taken that example to understand, to tell you what will be the exact one inside of this. But in most of the cases, if you can have any question, you can see that in such a way they are giving the nuclear state or nuclear number, so that the first excited or second excited state will be among these small energy gap, I mean small level, so that obviously there is no option to go from here to here. It should be from go here to here. Okay, like it is most probably the thing. But yeah, as you told me that is there any other option for that energy level calculation or what, there is no such option. Otherwise you have to remember this diagram, that is the one option. Or I can tell you, I can assure you that in most of the cases you can't have that type of critical questions. You can have a question which has a very small energy gap, or which has only one option to go to the higher level. Do you got your point, Shubham?
Yes, ma'am.
Okay. So like if you have any critical question, then you can tell me, but I think I can assure that like most of the cases you can have very simple one. But why I have taken that type of example, because I wanted to show you the energy gap is also important for the first excited state. Okay. Now coming to the second question, you can see that the second question is very similar. Speed and parity of the first two excited states of magnesium 1225. This is also very similar to carbon 613. But in that magnesium 1225, we don't have two options like that. We have only one option. I can show you that one also, so that you can understand there will be no need to remember the energy gap, or there is no need to calculate the energy gap between these two levels. Okay, so you can see that I am showing you so that you can understand. Can you hear? Okay, fine. Okay, so just come to that question so that it will be clear for all of you. See, within the nuclear cell model, speed and parity of the first two excited states of magnesium 1225 are. So here they are asking about first two excitation, not only first one, first two excitation. Okay. Now coming to the ground state. Obviously at the very first what we will do the ground state explanation. So I have written here the number of neutrons is 13, number of protons is 12. Now as proton we don't want to consider, so only the neutron number we want to consider. So you can see that the orbital for the ground state is this one, right? Now coming to the first excited state. What will be the first excited state? See here, here the last one was 1d 5 by 2, and above this there may be something, and below that what was that? 1p half 2. I mean this one, and there is 1, 2, 3, 4, 5. 5 was there in the ground state. It is ground state. Now coming to the first excited state. See, okay, in the first excited state, what will be it is? Obviously this will go to that one. because the one more probability was there that this can go here also, right? But you can see that again the energy gap 1p and 1d, 1p and 1d, see 1p and 1d, there is a most energy gap between these two, but 1d and 2s is a very small energy gap, then obviously 1d to 2s is most probable. But yeah, like for that also someone asked or someone is coming. Okay, so for that also you may have to note about the energy gap, but in most of the cases it is like that 1d 5 by 2 is there, then obviously it will go to that level because of that energy gap also you can say. But in most of the cases 1d 5 by 2 to the next one 2s half it will go, it will not go from here to here, that is the least probable, right? So like in most of the cases whatever in exam is coming, it is like that from the upper most energy state the nucleon will go to the next most energy state, that will be the case. But the exception is 6C13, that's why I have seen that one, I have shown you to that one. Now coming to this one, this is a very simple one, you can say that this is 2s half. So in that 2s half, so what will be the first excited state? The first excited state will be 1p half is there like that. Then here 1, 2, 3, 4. Now 4 is there and here 1 will be there. So 2s half and then 1d 5 by 2 is there. Now this is 4. This is 4 and this is 1. So which one will contribute to the spin and parity? This one will contribute to the spin and parity. So the spin will be half and the parity will be minus 1 to the power L, minus 1 to the power 0 because it is S. So that means it is positive, even parity. So for the first excited state, this is first excited state. For the first excited state, the spin and parity will be half and positive, even. Do you have any option on that? Half and even. So that means among these two options we can have one correct answer. But what will be the correct answer? We have to go to the next excited state also. So what will be the next excited state for that? The next excited state is like, what is the first excited state? First excited state is 1d 5 by 2, there is 4, and then 2s half, there is 1. This is first excited state. Now what will happen? This will again go to here, or this one can go to here. So what will be what will be the correct option? You can see here that 1d 3 by 2 and 2s half, there is a very small difference between that. That means 2s half will go to 1d 3 by 2. So where is that? So in the second excited state, 1d 5 by 2 will be 4, 2s half will be 0, and 1d 3 by 2 will be 1. Because you can see from that diagram, I just want to remove that one, all these things. Am I audible or not?
Yes, ma'am.
Okay, fine. So you can see here that 1d, so 1d 5 by 2, 2s half, 1d 3 by 2. So at the very first what was there? 1d 5 by 2. 1d 5 by 2 can go to 2s half, because this cannot go here because there is a very large energy gap in between that. Now this is for the case of first excited state. In the second excited state, what will be there? See here 4 right now in the first excited state. Here 1, 2, 3, 4 nucleon are there, right? And here only 1 nucleon is there. So it is most probable that this will go to that one because of that energy gap also. And another one reason is that 4 means it is already full. Full means like 1 is up, 1 is down, 1 is up, 1 is down. That means as a whole the total spin is 0. But here this is only 1, that means the spin is plus half, it is unstable compared to that one. So this don't want to go in that state, but this will go to the higher state. The higher state is what? 1d 3 by 2. So in that 1d 3 by 2, 1 will be there in next second excited state, and in that energy state no one will be there, and in that excited state 4 nucleon will be there. So this is the second excited state configuration. Now what will be the spin and parity for the second excited state? Second excited state means 1d 3 by 2, and for that AC is 3 by 2, and parity is minus 1 to the power 2, which is even parity. Why 2? Because D is there. So 3 by 2 and even will be the second one. What is that? Yes, 3 by 2 and even. So I told you that among these A and B the correct answer will be. So what is the correct answer? The correct answer is B, because from the second excited state we have 3 by 2 and even. I think it's a little bit complicated for you people at the very first day, but yeah, I have to tell that one. So like, do you understand? Hello, am I audible or not? Oh. Hello, again I got disconnected, right? Maybe there is problem in my internet. So like, did you hear that portion or not, or should I repeat again?
Ma'am, can you repeat it, please?
Okay, I just want to repeat again. Okay, fine. I- Okay. Can you hear me?
Yes, ma'am.
Okay, fine. Okay, so what I told, yeah, okay, let me clear this picture so that you can understand. No, like I was just telling whatever I told you in that first and second excited state. In that first excited state, at the very first, what was there? At the very first, there was 5. 1, 2, 3, 4, 5 in the ground state, and there was 2 in the ground state. As a whole, 7. Yes. This is the ground state configuration. Now in the first excited state, there may be one option from here to here or here to here, but you can see that this portion has a very less energy gap, so that means this will go here. So in the first excited state, this will be the configuration. That means here 1, 2, 3, 4 will be there. 1, 2, 3, 4, and this will be 1. So for the first excited state, what will be the configuration? The configuration will be like 1, 2, 3, 4, and here 1. This will be the first excited state configuration. Now coming to the second excited state. In the second excited state, what will be? This will come to here. That means here 1 will be there, and here 0 will be there, and here again 4 will be there. Now you can ask me why this cannot go here. For that reason, two answer will be there. The first answer is like, there was at the very first 4 was there, and here was 1. So you can see that as if it is a 4. 4 means 1 is up, 1 is down, 1 is up, 1 is down. That means as a whole the spin orbital angular momentum is 0, which is stable. Right? Can you hear me?
Yes, ma'am.
Okay. And here in that case, this is S equals to half, which is non-zero. That means this is unstable, more unstable than this state. So this can go quickly to the upper one. But also again you can also say this is one reason. The another one reason is that the energy level, what I told you. So according to the energy level also you can see that from here to here the energy gap is more than here to here. So obviously here to here we can go most probably. So that's why in the second excited state, what is the configuration for that? The configuration for second excited state is like 1, 2, 3, 4, and here is 1 and here is 0. Do you got the point? I think yes.
Yes, ma'am.
Okay. Okay, fine. So this is the thing. This was the question. So question number 6 is already done. Now coming to the question number 7. Yeah. In the question number 7, I think I have already mentioned that one in the previous class. But I think most of you were not present in the previous class. So I think I have to tell you again on that class also. See, this question in question number 7 is nothing related to the nuclear and particle physics. It is a very simple quantum mechanics, no, classical mechanics course. Okay. So what is the question? Question is, consider the classical case of a particle of mass this and charge this moving in a circle with angular momentum this. The magnetic dipole moment associated with this is something. So what will be the magnetic dipole moment associated with this particle? So this is a classical particle, right? So classical particle of mass is given, charge is also given. So it is nothing but a charged particle moving in a circle. So you know that when charged particle is moving in a circle, then it produces a magnetic field and there will be a magnetic dipole moment for that, right? So here we have m value, we have q value, we also have j, l value, like angular momentum. Angular momentum is also given. So we just need to calculate magnetic dipole moment, which is mu. So what is the expression for mu? For a very charged particle, mu has an expression that half qvr if it is moving in a circular orbit. Half qvr. Can you hear?
Yes, miss.
Okay.
Yes, ma'am.
Sorry for bothering you people because I did not understand when I was disconnected or not. So yeah, so the magnetic dipole moment expression is half qvr, right? So mu is half qvr. So what is given here? The given parameters are m, q and l. L is angular moment, orbital angular momentum. These three are given. But from that expression, how can I get qvr terms? Very simply, we just want to multiply m and divide m. Then you can see that mvr by m. Then what is this one? This is nothing but L. Now you can see that Q is also given, L is also given, M is also given. So by putting all these terms, we can have mu value. QL by 2M. Now putting this QL and M, then we can have mu value is like that. So see, I have already told you this is nothing related to nuclear and particle physics, right? It is a very simple classical mechanics thing. We have a charged particle, classical charged particle, and it is moving in a circle with a charge of 1.6 into 10 to the minus 19 coulomb, and it has an angular momentum is like that. What will be the expression for the magnetic dipole moment of that? Okay, got it? Yes, I think yes. Or should I disconnect? Did I disconnect it? No, fine. Okay, now coming to the second question, next question. In the next question also you can see that this is also not related to nuclear and particle physics. This is a quantum mechanics question. But as in your previous assignment it was given there, so that's why I have to discuss that in this question, in this course. So what is the question? In a scattering of electron of a nucleus, electrons of energy equals to 10 MeV are used. If these electrons are represented by the wave function phi equals to a e to the power ikz, where the position coordinate is along z cap the direction, the value of k is what? The value of k is wave number, right? So here basically they are asking about the wave number value where the electron has a energy 10 MeV and it is a wave, like it has a wave nature. So wave nature means obviously particle wave nature means it is coming out as a quantum mechanics thing. So now what will be the answer, like what is given here? Given is like E is given here and we need to know what is the value of K. So very simply we have a expression that E equals to h bar square k square by 2m. I think you all know this expression from the quantum mechanics. So what we will do, k is root over 2me divided by h bar square. Now h bar is already given, h bar is h by 2 pi and h is Planck's constant, right? So h you know, 2 pi is also you know, E you know. What is m? M means the mass of electron. The mass of electron is 511 MeV, right? That means if it is in electron volt, that 511 into 10 to the power 6 electron volt. So if you just put all these terms, then we can have the value of K, and it should be in meter inverse. So just focus on the unit so that it will give the correct answer. See, I have already written this expression. C is this one, 2me by h bar square. Now put m is this, then E is this one, then h bar is this one, then it is given as 1.61 into 10 to the power 13 meter inverse. Is it understandable? Hello? Arey. Hello?
Yes, ma'am.
I'm really sorry. So many times I got disconnected. It was not like that. I don't know why it is coming this one. So did you hear anything on that question or not?
Yes, ma'am. Yes, ma'am.
Okay, so I think it's a very simple question, so you can all know that answer also, like 2me by h bar square. Just put ame value, then we can have the value of K. Okay, it's a very simple one. I have already given the answer of that also, so you can just cross check with your answer so that it will be correct. Okay, now coming to the next question. I think I have mentioned this one, yes. So now coming to the next question. Next question a little bit tricky, not that much tricky. So in the next question we just see in an experimental measurement of the orbital angular momentum of deuteron. Have you heard about deuteron? Because in the first class also in the semi-empirical mass formula and then like nuclear and particle physics first lesson was on the deuteron, right? So in the deuteron there was something about like deuteron has one neutron and one proton in the nucleus or something there was mentioning, and then what will be the magnetic moment of deuteron, these things were there. Okay, so in an experiment the question is from that one only. It is not coming from the cell model, it is coming from the first question, first week assignment or first week lecture. Can you hear?
Yes, ma'am.
Okay. Okay, so in an experiment, the question is in an experimental measurement of orbital angular momentum of deuteron, 10,000 samples were selected. Approximately how many of them would have measured L equals to 0? H by 2 pi. H by 2 pi is the unit, that means H bar. H bar is the unit of that momentum. Orbital angular momentum. So approximately how many of them would have this one? So I think you have heard that one, that deuteron has L equals to 0 and L equals to 2 simultaneously. I mean it's a hybrid orbital angular momentum state with two orbital angular momentum values 0 and 2. But 0 is as 96% and 2 is as 4%. So now you can have a very simple calculation, that they are asking that we have total 10,000 sample, then we have total 10,000 sample, and among them how many has L equals to 0 pi, 0 h bar? That is the question. So what we will do, we will just do a simple mathematics on that. See, you can see that, like if 100 samples are there, then among that 96 are L equals to 0. Then 1 is 96 divided by 100, then 10,000 we have the samples, then 96 into 10,000 divided by 100, then it is 960. 10,000, okay, 9600. That means we have 906,000 samples with L equals to 0. Okay, so the correct answer will be 9600. Do you understand? Like, as L equals to 0 has 96% contribution, L equals to 2 has 4% contribution, then L equals to 0 h bar means it has, among the 10,000 sample, 9,600 sample is with L equals to 0 h bar, and if rest of the things are L equals to 2. Do you understand?
Yes, miss.
Yeah.
Yes, ma'am.
So the second question is very similar to that one. In an experimental measurement of the orbital momentum, these samples were selected. Approximately how many of them would have measured L equals to 2 h bar? Obviously, you have already calculated that 9600 was L equals to 0 state. Then how many will be L equals to 2 state? Because in deuteron only L equals to 0 and 2 are applicable. So that means the rest of the things means 10,000 minus 9,600, which is 400. So 400 samples will be L equals to 2 h bar. Fine? I think it's fine for all of you. Yeah, I have already mentioned here this one. Someone asked something or what? Oh, D. Yeah, thank you. Yes. So this is the D one, right? Now coming to this last question. Last question is a little bit big, not tricky, but big. Okay. Very simple. Whatever we have done from the last 1 hour, it's the similar one. Predict the ground state spins and parities of aluminium, sulfur and argon. Now you have to tell me the answer. I will not tell you the answer. So you have to give me the answer of these three. What will be the ground state spin and parity? Because we have already discussed these things so many times in this class, right? So, like, I just want to write here the configurations of that so that you can have an idea. Number of proton is 13, number of neutron is 27 minus 13, which is 14. Now what is this one? Sulfur 1633, number of proton is 16, number of neutron is 33 minus 16, which is 17. Now argon 1841. So number of proton is 18, number of neutron is 41 minus 18, which is 23. No, 23. 23. So now you have to tell me what will be the ground state spins and parity for each and every one. I can give you 5 minutes for each and every question. So like aluminium 1327, I can give you 5 minutes is more, 3 minutes. Within 3 minutes you can give me the what will be the spin and parity of aluminium 1327. Can you do all of you?
Yes, miss.
Okay, so just to do that one, I think it is 23, so I can ask after 2 minutes, 25.
5 by 2 even.
Oh, you have already done. Great. So aluminium, let me check, I have already done here. Okay, I think I have to give one more time to do all people these things. In the meantime, you can do other 2 terms also. Oh, someone has written that one. Okay. I think you people have already done these things. Okay, so what will be the first one? The first one is aluminium 1327. The answer will be 5 by 2 positive. How many of you have corrected that one? 5 by 2 positive. Okay, positive means even. Yeah, someone has written here Nilu 5 by 2 positive. Yeah, thank you. Good. Now coming to the next question. What is sulfur 1633? What will be the answer of that?
3 by 2 positive.
3 by 2 positive. Yeah, right. And what is argon 1841?
1 by 2 negative.
What? Sorry, I can't hear you. Am I disconnected or what? No, I'm not.
7 by 2 negative, ma'am.
7 by 2 negative. Okay, yeah. 7 by 2 negative. I think I have heard 1 by 2 negative, so that's why. 7 by 2 negative. Yeah, 7 by 2 negative will be the correct answer. Okay, so all of you have done it, or I think obviously as it is very simple one, so. Okay, so can you tell me what will be the first excited state of argon 1841? I can give you that table also so that it will be good for you. The table is where? This one. Yes. You can take the help of that table also. Argon 1841, you have to tell me the first excited state of that. Okay. Where is my pen? Pen is
3 by 2 positive.
3 by 2 positive. Okay, what was the last one? Can you please tell me? 1F 7 by 2 what? I mean, in ground state, what was that one?
7 by 2 negative is a ground state.
No, like how many protons, I mean, how many nucleons were there? 1F 7 by 2, then what was there? In the ground state. 3 by 3, right? Oh, 3, yes, 3. Okay, now this was 3. 1, 2, 3. Now in the first excited state, you told me that this will be 2 and this one will be 1. Now can you tell me what will be the second excited state? This is the first excited. The first excited.
It's 5 by 2, ma'am.
Yeah, 5 by 2. And what will be in that 1, 2? No, like
negative.
What will be in that state?
That state 0.
0. That state 0. And here it will come here. And there will be 0. There will be 2. Because you know that 2 means like 1 is up, 1 is down. That means it's the most stable. And also you can see from that energy gap also, it has a little bit more energy gap. Okay, fine. So 2 excited state is also done. First 2 excited state. First 3 excited state also you can do. I think first 3 excited state means like at that time it was here. So here will be that and these 2 will be there. Like that. Now in the 4th excited state also these can go here, right? But in the 5th excited state, you can see that this energy level is little bit more than this one. Then this can go here and this will remain here. But obviously like for you people not that much complicated will be there, but I just wanted to know you that what is the difference between that energy level and energy gap and all, right? So here you can, that 5th excited state, you can see that this will not go here, this will come here, because the energy gap between these 2 and these 2 are like this one is small one compared to that one. Got it? I think yes. Or I have disconnected. No, I did not disconnect it. So like do you understand like that energy gap consideration? Yes, right? So like obviously the 5th excited state, I think no one will ask about that one. Only first 2 or first 3 at most they will ask. So if they are asking for fifth excited state also, then you can have to think a little bit more that which one will go to the next higher level. Okay. Okay. So I think for today it was too much, and we will meet in next class. If you have any doubt on that class, I mean on that session, whatever we have taught in this class, you can ask me. Otherwise, we will stop. I mean, I had that much questions in my hand, so that's why all the questions is already discussed. So I'm just going one by one the questions again, so that if you have any question you can ask me right now. See, this is that question. Then coming to the second question, this one is second question. Then this is third question. Then this is fourth question. This is fifth. This is sixth. This is seventh. This is eighth. This is ninth. This is 10th, and this is 11th question. Is there any question on that chat box? No, there is no question in chat box. So, do you have any doubt or something? You can ask me, or we will meet in next class.
Hello, ma'am.
Yes, tell me.
Ma'am, I have explained that how to remind that diagram. If there is no formula, if someone will ask question here, tell me that 6 excited state or 7 excited state, without taking help from the diagram, how can I tell it?
Yeah, like I told you, na, like let's say, I mean, in most of the cases, the questions will be like from here to here. It is not that from here to here the questions will be asked. So from here to here, obviously there is only one option, that you have to go from here to here only. Like that may be one probability, but it is not the exact answer of your question. Exact answer of your question will be, you have to remember this diagram. See, like here you can see that, okay, I can now tell you one thing also. 1S, 1P, there is a very large gap. Then 1P, 1D has also a large gap, but 2S, 1D is very small gap. I don't know how to remember, but you have to remember. Sorry to say, but yeah, but as per I understand that most of the questions you have to do from the last energy level. I mean, you have to put that nucleon to the most one, to the next one. That is the most general case, but some exceptions are also always there. So for that you have to remember this diagram.
But if someone has drawn this diagram, if obviously they use some formula or some trick
Yeah, they use
for the calculation.
Yes, they use some formula. This is spin orbital interaction formula. This is a very big one. I think I have sir already taught you that one. But see, in exam or in any competitive exam, if you are going to calculate this with putting this formula, the data and all, then it will take so much time, right? But yeah, obviously you can get this diagram from that formula, but it will take so much time for that. But it's better to at least remember these numbers. These numbers you have to remember for always, right? But we are just considering right now, we are just concerned about the energy levels. How do we understand the energy level gap? That is the main question of yours. So for that you can have to otherwise remember, or otherwise you can calculate. The calculation of that energy level spin orbit momentum is a little bit tricky one. I have the expression of that one also. Just put these terms here in that expression, then we can have the energy gap formula. like okay, I can show you here spin orbit interaction. If you just search here nuclear cell model, I can tell you. Okay. Nuclear cell model, then just go to the Wikipedia, then there is one expression. Obviously you can search in your books also, textbook also. See, in that including a spin orbit interaction, there is one expression. I have seen that expression. Where is that expression? There is an expression for the energy gap calculation, but it's a little bit tricky. So that's why I don't wanted to tell you. It was the energy. See, this one is there. 2n plus L plus 3 by 2 into h bar omega. I mean, h bar omega is a very simple one, but like you can have like, if you just push 2n plus L plus 3 by 2 this expression, then we can have like n1 L1 n2 L2, then delta E equals to the difference between n1 L1 n2 L2 expression. So that we can have the expression. You can see that this is the actual one, whatever we were talking about. So 0s, I mean S, P, D, then S again. So these are the expression, energy level. Then how these are coming? These are coming from the expression is this one. So if you just calculate this one for A and L, you have the N and L value, right? I have told you that what is the which one is N1, N, and which one is L in that notation. So if you just put that N and L value, then we can have the energy level, I mean difference of that energy gap.
Yeah, okay, ma'am.
This is a very simple, not that much simple, but yeah. Yeah, this is the thing, this is the case, yes. Then just put that N, L value. N and L value you can understand from that expression, right? Which one is N and which one is L. Let's say I have 1P 3 by 2. Which one is N and which one is L? N is what for here?
The P value is L and the 1 is N.
N is?
N is the 1 P, na 1.
And P is also 1 and S is 3 by 2. So here in the calculation of delta E, I think the S is not needed. So like we just have to put the N value and P value so that we can have the energy gap delta E of that. I think I have had the exact, this is the simple one, there is no S condition. So this is not the exact one. I will tell you exact one in the next class because I don't have right now that expression. So there you can have N, L and S combination also, so that you can have the exact energy gap between these two energy state. Okay, so I will tell these things in next class, no problem. Because you can see that here in that expression there is no S dependence. So that means all the S state has the same value, right? In that, from that expression we can say that there is no S expression. That means spin expression is not there. So that means all the spin is like same value here. But it is not like that, right? In that figure you can see that this S 2S half and let's say this 3S is different. But yeah, like obviously this is also another one. I have the expression, but I will tell you in the next class.
Same, it is difficult to calculate 1P 3 by 2 and 1D 3 by 2.
Yes, yes. Like let's say this one, 1P and 1S. 1P half and 1P 3 by 2. Yes, ma'am. From class. 5 minutes. So for that 1P half and 1P 3 by 2, you can see that like P is 1 here, right? And for S is different. So here you can see that 1P half and 1P 3 by 2 should have the same value. because it is not true. I mean, from that expression it is showing that n is also same and l is also same for these two, then obviously these two have the same expression, but it is not true, right? This has a very small energy than this one, so we have to have the exact expression for that. Do you got what I am telling, like that difference?
Yes, ma'am. Yes, ma'am. I'm getting it.
Yes. So like for that case we can have a very same energy level, but it should not be like that. I have the expression, but I will tell you in the next class, because I think I don't have that now. So I will tell you.
Okay.
No problem. Yeah. So from that expression you can tell, but yeah, like I think I can assure you that in the most of the cases you have to just do that from the last energy level to the most, next energy level. That is the most, in the most of the cases that is the thing. But yeah, obviously some exception is there. So. Okay, so I think there is not that much questions again. So should we conclude the session? We will meet in the next Sunday 3 to 5. Okay. And that video will be recorded. It is already recorded, so the video will be uploaded in the YouTube channel. If you just want to see that, let's say I am writing here YouTube, okay, then just write my name here. I can tell you, just write my name here. You can see, yes, this is week 0 and week 1 assignments. It is 6 days ago, right? So this is 6 days ago. This was the first first video for this session. And otherwise you can go here also, you can see all the videos here. These videos are the previous previous year, previous session, but if you just go here, this is the last week question answer. Okay. Oh, someone asked me something. सेकेंड स्टेट और थर्ड स्टेट में इलेक्ट्रॉन कैसे ट्रांसफर होगा वो एक बार समझा दीजिए. सेकेंड स्टेट और थर्ड स्टेट में इलेक्ट्रॉन कैसे ट्रांसफर होगा? कौन सा वाला? सेकेंड स्टेट थर्ड स्टेट में, सेकेंड स्टेट थर्ड स्टेट क्या बोल रहे हो, एक बार बोल सकते हो? कैन यू प्लीज अनम्यूट योरसेल्फ? नीलू, लास्ट प्रॉब्लम, कैन यू प्लीज अनम्यूट योरसेल्फ? हेलो, Neelu is there or not? Oh, okay, my problem. Okay, last problem, second state and third state में इलेक्ट्रॉन कैसे ट्रांसफर होगा? Second state means like second excited state to third excited state you are telling, right? I think yes. Okay, yeah, okay, got it. So yeah, just let me tell you. Yes, in the last problem, what was the last problem? There was argon 1841, alright. So in 1841 the ground state was 1f7/2 3. So in the ground state what was there? 1f7/2, where it is? Yes, here. So in the ground state 3 nucleon were there in the 1f7/2 state. This is the ground state. Now coming to the first excited state. What will be in first excited state? In first excited state you can see that this one can go here. That means in the first excited state these two will be there and one will come here, right? So that means this is the first excited state. Now I am removing the ground state. This is the first excited state. Now coming to the second excited state. What will be the second excited state? Second excited state means this one come to here. That means here will be 1 and here will be nothing. And here will be 2. So I am just removing first excited state so that it will be clear. So, so this is second excited state. This is second excitation. Now coming to the third excitation. What is third excited? Here to here. This one will be there and there will be nothing. So I am just again removing the second excited state. In the third excited state, I think it was there, right? I forgot. Here to here, first, second, third. In the third excited state, this one will be the configuration. Now coming to the fourth excited state. In fourth excited state, this will come here, and there will be nothing. In the fifth excited state, this one will not go here, but this one will go here because the energy state is little bit small than this portion, right? So that is the thing. Do you understand, or is there anything? Like you were talking about second excited state and third excited state. So second excited means this is first, this is second, this is third. Okay, that means second excited means from here to here. This is the thing. Okay. Okay. Thank you.
Thank you.
Okay. Yeah. Do you have any question? Someone told something. I think no. Okay, so if you people don't have any question, then we can close our session today and we will meet in the next week. Okay. Bye bye.
Thank you.
Thank you, ma'am.
Bye bye. Thank you.
Thank you, ma'am.
Thank you, ma'am.